Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Department of Mechanical Engineering, Hyderabad, India. In this session, we are going to study how to solve problems on principal stresses. So, principal stresses are the stresses on which the shear stress equal to 0. Here, in this problem, we have to find out the normal stress and the shear stress. And also, we have to calculate the maximum shear stress at the point. So here at a point in a stressed body, the principal stresses are given as 100 meganewton per meter square. It is in tensile, and 60 megapascals, and it is in compressive. So we have to find out the normal stress and shear stresses, normal stress and the tangential stress on a plane inclined at the angle of plane is 50 degree to the axis of major principal stress. And also we have to calculate the maximum shear stress. There are three objectives are there. Normal stress, number one, normal stress. Another one is shear stress. And the third one is maximum shear stress. Normal stress, shear stress, and the maximum shear stress. So here the analytical solution for this is sigma n, that equal to average of the stress sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta. And tau, tangential stress, that equal to sigma x minus sigma y by 2 sin 2 theta. And here one more thing is that the sigma r, it is not asked here, that is the resultant stress equal to under the square root of sigma n square plus tau square. So for this, the given data here, it is given as sigma x equal to maximum of those two values, that is 100 megapascals, 100 meganewton per square meter, and compressive stress sigma y, it is minus 60 meganewton per meter square. It is in compressive, that's why it is negative value, and it is sigma x, it is in positive. So here the angle of theta, that is value of theta is 50 degree. So if you draw the diagram in the plane, then the stress indicates there is a direction of, and the maximum, it is making with the maximum principal stress, that is 50 degree. It is sigma x. Sigma x is 100 meganewton per meter square. And the compressive given here, it is not tensile, and the compressive in y direction, that is 60 meganewton per meter square. Is the data in pictorial presentation. So in pictorial presentation for the given data, the figure will be visible. Now the formula, we know that sigma n equal to, that is normal stress. The normal stress sigma n is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 times cos 2 theta. Alright. So substitute over here what is sigma x value, sigma y values. The sigma x value, that is 100, sigma y is minus 60. Sigma x minus of, in the place of sigma y minus 60, if you substitute, then the calculations here obtained as 100 plus minus of, this is sigma y is the compressive, that's why negative 60. 100 minus of minus 60, that is 100 plus 60 by 2 cos 100, that is theta is 50 degrees. 2 theta, 2 times 50, that is 100 degrees. So the value calculated is the positive, that is 6.1 meganewton per square meter, that is megapascals. 6.1 megapascals in the normal stress for the given values of stresses in x direction 100 MPa, and y direction compressive stress, that is 60 megapascals, and the angle made for the inclination of the plane with the major principal plane is 150 degrees. Next, the next objective is the shear stress. The shear stress formula for this is that the shear stress equal to sigma x minus sigma y by 2 sine 2 theta. Sigma x, that is 100, minus of sigma y, minus 16 by 2 sine 2 times theta, 50. So 100 plus 60 by 2, that is 80 sine 100. So if you substitute those values, then it is occurred as 78.78 meganewton per square meter. The shear stress is found as 78.78 megapascals is the positive shear stress. So the positive shear stress here it is, okay, it is in clockwise direction. And the third objective here it is the maximum shear stress. The maximum shear stress formula for that is tau maximum equal to sigma x minus sigma y by 2. This is the formula. So what is sigma x? That is 100 minus of sigma y minus 60 by 2. That is 80 megapascals. That is the shear stress maximum. The shear stress is occurred as 78.78 megapascals, and the maximum shear stress is calculated as 80 megapascals. So how can we know that this value is right or wrong? Here the maximum shear stress is always larger than the value of tangential stress or shear stress. Now these are the three objectives are calculated, and one more thing here, sigma n equal to 6.1 megapascals, sigma n, that is 6.1 megapascals. Sigma n equal to 6.1 megapascals and tau equal to 78.78 megapascals. Here, these are the three objectives are asked in this problem. But suppose if they asked that is what is the resultant stress and what is the angle of obliquity phi. Suppose if they ask what is the resultant stress, sigma r equal to under the square root of sigma n square plus tau square. What is sigma n square? 6.1 square plus tau square, 78.78 square. So if after calculation this value comes, that is the resultant stress. What is the angle of, with what angle this resistant stress is acting? The resultant stress action of that angle is nothing but angle of obliquity, that is tan inverse of tau by sigma n. Tan inverse of tau by sigma n, that is tan inverse of, what is the tau value here? 78.78. What is sigma? 6.1. So this value gives the angle of obliquity, and sigma r gives the angle. Sigma r gives the resultant stress of sigma n and tangential stress, shear stress. These are the objectives we calculated here in this problem. The three objectives are mentioned, but two more objectives are also calculated by using the same data. Now, what is the novelty of this problem in comparison to before problems? So, the novelty of this problem is that here the compressive the stress in x direction is tensile and the stress in direction y is compressive. There is a novelty of this problem in comparison to previous problems. When there is the compressive stress, so the point is that when there is the compressive stress, the direction of compression is towards the cross section, the compressive stress. We proved what is the sigma x values, the sigma n and tau and sigma r. These are calculated or proved by considering the stresses in axis x and axis y are tensile. That's why by considering the tensile stress, we considered what is the maximum what is the normal stress, what is the shear stress, and the sigma r. These are the formulae for the conditions of when sigma x and sigma y are tensile in nature and theta, it is made with the angle of inclination with the major principal plane, with the major principal stress. That was the angle. Under those considerations, we proved this formula, that is sigma n equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 times cos 2 theta, and the tangential stress tau equal to sigma x minus sigma y by 2 sine times 2 theta, sine 2 theta. So suppose, a little bit discussion, suppose here that this 50-degree considered, the 50 degrees, the angle of the plane inclined at 50 degree to the major principal stress. Suppose if this 50 degree is to the axis of minor principal stress, then how to consider it? Here the theta is the angle of inclination, the plane inclination to the axis of major principal stress. This is the theta here. But suppose if they mentioned this angle theta with the minor principal stress, then this theta becomes 90 minus theta. You have to consider. So in that manner we consider it. Now we solved so far analytical method. Now we are going to solve with the graphical method. In graphical method here, what is sigma x value and sigma y values, that is compressive minus 60 MPa. Sigma x values are 100 megapascals. So how to start this sigma x and sigma y? Take a scale, and here the sigma x is tensile and sigma y is compressive. So these are the values. How to find out what is sigma n, what is the tangential stress? We can calculate also sigma r, that is resultant stress, and angle of obliquity can be calculated. Now when the one sigma x is positive tensile and sigma y is negative, take a scale, the 10 megapascal equal to the scale considered here. Scale that is 10 megapascals equal to 1 centimeter. Then sigma x 100 megapascals becomes 10 centimeters. Sigma y becomes minus 6 centimeters. Now take any point O, horizontal line from O to OL, that is sigma x. Try line, that is sigma x, that is 60, 100 megapascals. Mark it as LOL. Is the tensile direction, it is all tensile. And the negative direction of the O is compressive zone, compression force zone. Now on this here, from O, you consider the sigma y, that is minus 6 centimeters. This point is M. This is the point M. From O and L, the midpoint becomes, take a midpoint, that is N, center is the N. Draw a circle from this distance, this is the 10, it is 6, 16 means 8 centimeters radius, you draw a circle. So you have to use, I am showing you manually. So after this, what to do? The end point, with the help, we take a protractor. This is the reference line NL. The angle of inclination here, it is 50 degree. So 2 theta times, they make it as 100 degrees. Make it 100. That is crosses 90 approximately. It is 2 theta, 100 degrees. So project on this point. This is the P. Sorry, this is the P. It is Q. The distance from PQ gives the tau. The PQ gives the shear stress, and the distance from OQ, that OQ gives distance from O to Q, that OQ gives the normal sigma n. And P to O you join again, O to P. This OP gives the sigma r. O to P gives sigma r. The angle of inclination with O with P gives angle of obliquity. So here the values, the sigma x and sigma y having a close relationship. Now, how the diagram? This is the procedure to find out the normal stresses and shear stress values by using graphical method, that is called Morse circle method. So the figure will be looks like that. Now it is a sigma very close OQ distance gives that the OQ is the sigma n, that is 6.1, and tau max is 80 megapascals. Now what is the first step? Is the point O to L, that is the step 1, that is sigma x. OL with the sigma x, that is sigma x. Next OM, sigma y is the compression, that's why it is in compressive zone, negative zone. So make a midpoint, make a center N, take a radius of NL or NM, take a radius of NL or NM, draw a circle. That circle is known as Morse circle. Morse circle. This is the circle, Morse circle. So after this, take a distance from N is the center, NL is the reference line. Take an angle of 2 theta, that is 100 degrees. Mark point P. Mark point P. By taking an angle of 2 theta, 2 times 50, that is 100 degrees. Now join line NP, joining line N to P. Now project this point P on the axis on the line OL, that is OQ. So this PQ height gives the shear stress, the stress 78.88. This PQ height gives the shear stress tau value. Okay, PQ, height of PQ gives the tau value, and the distance from O to Q gives sigma n value, and joining OP gives sigma r value. Sigma r, that is joining OP, sigma r value. And the angle of inclination of OP, that is angle of obliquity, that is the phi. So the values for this we have observed are sigma n is 6.1 megapascals in tensile, tau 78.8 megapascals in shear, and tau maximum. What is the tau maximum? Tau maximum, that is 80 megapascals. Okay, NZ, what is the tau maximum here? Here NZ is the maximum value. That is the tau maximum, 80. So this is the graphical method. So we found out what is the normal stress and what is the normal stress, the tangent stress, and resultant stress, angle of obliquity, and maximum shear stress for the given tensile stress. In x direction is 100 megapascals, and in y direction it is 60 megapascals in compression. So coming to next problem, here The novelty in this model, so far we covered problems of when there is for direct stresses, for the cases of direct stresses sigma x and sigma x, sigma y and sigma y, and making an angle theta. So here sigma x and sigma y are tensile in nature. Tensile. Sigma y also in tensile. The angle made here, it is theta with the maximum principal stress at the sigma x value. Theta. Now, another model we covered has, here it is. From this model, from the first model, we found sigma n and tau, sigma r and phi. Sigma n means normal stress, tau shear stress, sigma r resultant stress, and phi is angle of obliquity. The next model we covered, sigma x is a tensile in nature, whereas sigma y is in compression. Sigma y is in compression nature. Sigma x is in tensile in nature, sigma y is in compression. So here the angle made of inclined plane theta with the maximum principal stress. But here one more thing what we have studied is that we've calculated for all the cases normal stress sigma n, shear stress, or another name of shear stress, here it is known as tangential stress, and resultant stress, tau maximum shear stress, and angle of obliquity. These are all calculated by using two methods. The two methods are, one is analytical method and another one is graphical method. In the analytical method, we use the concepts of equilibrium conditions. By using equilibrium conditions, that is sigma fx equal to 0, sigma fy equal to 0, by using these two conditions, we calculated a derived what is normal stress on that inclined plane. Normal stress on the inclined plane by assuming that the sigma x and sigma y are in tensile nature. What is the normal stress here? Which acts normal to the plane, that is sigma n. Tangent shear, it is tau. The sigma n, that is equal to sigma x plus sigma y by 2. The sigma n is in terms of sigma x and sigma y plus sigma x minus sigma y by 2 cos 2 theta. And another value tau is sigma x minus sigma y by 2 sin 2 theta. So in this manner we derived the formulas of normal stress and shear stress. But here the case study is that direct stresses which are in mutually perpendicular to each other but tensile in nature. There is the analytical method. What is sigma r? Sigma n and tau. What is sigma r? The resultant stress sigma r equal to sigma n square plus tau square. Sigma r equal to sigma n square plus tau square under square root of sigma n square plus tau square. That is the sigma r. It is sigma r, it acts in the direction. Now, what is the inclination of sigma r with the sigma n? that angle is known as angle of obliquity. That angle of obliquity that equal to tan inverse of tau by sigma n. This is angle of obliquity. Angle of obliquity means the angle with that resultant stress, the direction of the resultant stress. The magnitude of the resultant stress sigma r is under square root of sigma n square plus tau square. This is the direction. This is the magnitude formula. What is the direction of this resultant stress sigma r? That direction is tan inverse of tau by sigma n. So these are the formulae derived by analytical method with the help of equilibrium conditions. Equilibrium conditions here, algebraic sum of all the forces normal to the plane, normal to this inclination plane, that is sigma n in the direction that equal to 0. And another one is algebraic sum of all the forces acting tangential. This is the tangential and normal. The tangential direction equal to 0. So by using these two equilibrium conditions, we derived the formula sigma n, tau, sigma r, and phi. One more thing is that maximum shear stress tau max equal to sigma x minus sigma y by 2. How this tau maximum derived from shear stress equation, that is sigma x minus sigma y by 2 sin 2 theta. This shear stress becomes maximum when theta equal to 45 degrees or 2 theta equal to 90 degrees, sin 90 equal to 1. So the tau becomes tau maximum when theta equal to 45 degrees. The next method we derive here, that is graphical method. That graphical method, here it is. We use it here, graphical method. Graphical method is, another name is called Morse circle method. That is known as Morse circle method. By using this Morse circle method, how to start Morse circle method? The input parameters, given parameters are sigma x value, sigma y value. Okay, by considering here Morse circle method, we are considering only given data is sigma x and sigma y, mutually perpendicular stresses and theta value. The output parameters, outputs are sigma n, tau, sigma r, and angle of obliquity phi. So the methodology for this graphical method is, first take any point O, any line, any vertical line. Take a scale of sigma x in terms of megapascals into linear scale in terms of millimeters or centimeters. Sigma x in tensile, considering here sigma x, sigma y both are in tensile nature. Then to the positive direction, take sigma x value. Suppose it is point L. Sigma x value, it is L, point L. OL is sigma x. From O, sigma y is also in tensile. Take sigma y value from O to M. This is M. OM gives a sigma y. Make center of ML, that is a center N. Draw a circle either with the radius of either NL or MN. That circle, draw a circle. This circle is known as Morse circle. Alright. Next, take this point N and the angle of inclination is theta here. Take 2 theta. If it is 10, 2 theta, angle of inclination. Mark the point P. Join N to P. Now projects This point P projects this point P on OL line, that is Q. This PQ gives shear stress, that is the tau, and whereas OQ gives normal stress, sigma n. The angle of inclination, join the line with O to P. The angle of inclination of OP with OL gives angle of obliquity. And the distance, the length of OP, that is hypotenuse, gives the length of OP gives sigma r. So here the distances OQ gives the value of sigma n, PQ gives the value of tau, OP gives the value of sigma r, and the angle of inclination of POQ gives angle of obliquity. So these are the methods we have studied so far. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.